Around 200 years ago, a Danish physicist called Hans Christian Ørsted made a discovery which is one of the most important in the history of electromagnetism. Ørsted's experiment involved a current-carrying wire and a needle compass. Ørsted noticed that when you brought the current-carrying wire near the compass needle deflected. Ørsted had demonstrated that electricity and magnetism were linked. In fact, all electric currents produce magnetic fields. A few years later, Michael Faraday showed that changing magnetic fields could produce electric currents. The current induced in a coil of wire depends on the rate of change of magnetic flux through the coil. Here are a few cool examples of Faraday's law of induction. This is a piece of yttrium barium copper oxide superconductor, and I'm going to use it to demonstrate how Faraday's law of induction can be used to levitate objects. Here I'm going to use some liquid nitrogen to cool the superconductor down to around minus 200 degrees centigrade. When superconductors like this are cooled down to low temperatures, they have zero resistance. So, once the liquid nitrogen stops boiling, the superconductor will be at a temperature of approximately minus 200 degrees centigrade. And if I bring a magnet close to the superconductor, the increasing magnetic flux will induce currents on the surface of the superconductor which will try and oppose the change which produced them. So those induced currents will create an opposing magnetic field to try and force the magnet away, and it will levitate. Because the superconductor has zero resistance, the induced currents can respond instantly to any change in the position of the magnet and oppose any changing magnetic flux. Even if I spin the magnet, the induced currents will respond to levitate the magnet above it.
So here's another example of how we can use Faraday's law of induction to do something cool. This is a high current transformer. It's used to generate thousands of amps. Now, like any transformer, it consists of two coils of wire, one we call a primary and one we call a secondary, all wound around a steel core. We pass an alternating current through the primary. This produces a constantly changing magnetic flux in the secondary, which according to Faraday's law, induces a current in the secondary. Now we're going to use this current and we're going to drive it through this poor little fork here. Now the amount of current induced in the secondary coil is determined by the ratio of the number of turns on the primary coil to the number of turns on the secondary coil. So we have 300 turns on the primary coil and only about 3 turns on the secondary. So that gives us a ratio of about 100. So we should get 100 times more current through the secondary coil, which is what we're going to pass through our fork. So even though the current in the secondary coil was stepped up by a factor of 100, the opposite happened to the voltage.